So instead of a block, I just drew something round. But this whole thing is traveling in a circular path with a speed of 2 radians per second. Now, you actually have done a lab that showed this. In the lab, you spun the weight about your head, and then if you pulled on the string, you made the radius smaller. You should have seen clearly that when you make the radius smaller, the speed of the object increased. So everybody who did that lab and was paying attention was able to see that, mostly because you tried to get your head out of the way. So that's what this problem is about. Somebody pulls on the cord and shortens the string so that after a moment, the string has been shortened to 0.2 meters. The mass stayed the same, but the angular speed probably changed. I say probably, but it's conservation of momentum. So the angular momentum before has to be equal to the angular momentum afterwards. Since there is a change in the moment of inertia, this is similar to what happens when the ice skater brings her arms in. Now, this particular problem has an issue that you may or may not remember how to deal with, and that is how to calculate the moment of inertia. For an object that's got a rotational axis that is far away from its center, in this case, way far away, their moment of inertia becomes that of a point mass. This is the moment of inertia of a point mass. It's the same as a ring, but you have to memorize this one. The moment of inertia of a point ring or a point mass won't be given to you. But anytime an object is rotating some distance far away from itself, then it's treated like a point mass. That's worth putting in your notes. In the case of this problem, the mass doesn't change.
Can you repeat that one more time?
Sure. Now, in this problem, the moment of inertia dramatically changes because you shorten the string. Because the moment of inertia dramatically changes, the angular speed also changes. The moment of inertia before is 2 kilograms located at a distance of half a meter away. So that's the moment of inertia before, which works out to be 0.5 kilograms meters squared. Afterwards, you shorten the radius to 0.2. The mass doesn't change, but the radius is substantially changed. This will be a moment of inertia of 0.08. It's a big change. If we consider that the moment of inertia became smaller, going from 0.5 to 0.08, the angular speed is going to have to change to compensate. The angular speed was 2. You can use this to find out the final angular speed after you pull on the string. This goes out to be 12.5 radians per second and would have been the answer to question 43. Now, you have to be able to do this part of the problem to answer question 59. If you couldn't do this, and many of you couldn't, I looked at your homework, you had no way of doing 59. Now, I would follow this question up with the same questions that are in question 59. I would ask questions like, what is the change in kinetic energy of the system? This system conserves momentum. It does not conserve energy. So I would ask again, question B, what is the change in kinetic energy of the system? Of course, I probably wouldn't ask it like that. I would probably ask it in version C, which was how much work is being done. That's probably what I would ask. How much work is being done when you shorten a string? Although B and C are the same answer, most of you would see question C as being confusing because you will have forgotten that work means change in energy. And because you tend to forget that, you start writing things like force times distance, and you get your problems wrong. But that's the last resort on how you calculate work. You should always consider change in energy first. This problem, when it goes faster, it changes the energy. In fact, I can imagine a question D, which has nothing to do with this chapter. But a question D would be how much tension is in the string. And I would most certainly want to ask that on a test because it brings together stuff from first semester. The tension on the string was what you did in your lab. And if you don't remember that, net force is going to have to equal MAC, where that is the centripetal acceleration. So, with that being said, let's take a look at question 59. 59 begins with a bug of known mass standing at distance d from the axis of a spinning disk. So let's write all of those things out. I have a spinning disk. That's not a spinning disk. I have a spinning disk. And the bug is a distance d from the center. The disk has a mass of md and a radius of rd. The bug begins some distance d away from the center and has a mass m. So there's my bug. Now, what they tell us is that currently the disk is rotating at a frequency of some revolutions per second. They don't tell us what it is, but they give it to us in revolutions per second. They're trying to confuse us. It says after the bug walks out to the edge of the disk and stands there, the disk rotates at F final. All right, so the bug actually starts inside and walks to the outside. That's just a little change. We'll put this as the bug starting position. And he walks to the outside, which is located at the edge of the disk. Now, here's what you guys probably aren't thinking of, and I think you need to. The disk and the bug have a single moment of inertia. It would be the moment of inertia of the disk plus the moment of inertia of the bug. They just add together. You would probably need to look up the disk in a chart. Now, if you have that chart handy, great. If you don't, on a test, it would be provided. But since you were doing this for homework, you had access to this chart and your notes where it's been given to you that a disk is 1/2 mr squared. The bug, however, is a point mass. And a point mass is mass of the bug times where it is. It starts a distance d away from the axis. I'm going to pause here. I'm getting back to this. And this is the part that I'm trying to emphasize by being very slow and deliberate. But This part doesn't change. The disk's moment of inertia stays the same. But this part does. The bug walks to the edge. So there's a moment of inertia before, and there's going to be a moment of inertia after. And the moment of inertia after is going to be 1/2 md rd squared plus mrd squared, because the bug walked out to the edge of the disk. And by the way, this is what I have in mind for your test. The difference is I make this a kid's merry-go-round with 4 kids standing on the edge, and they walk towards the center. And I ask what happens. You should be able to realize that as the bug walks to the outside edge, the disk slows down. You should know that not intuitively, that's the wrong word. You should know that qualitatively, that as the bug goes from the inside to the outside, he increases the moment of inertia of the system. Because he does, there has to be conservation of angular momentum. So if the moment of inertia of the bug and the disk gets bigger, then the angular speed has to get smaller. There I'm trying to make it like by making the letters bigger and smaller. You can follow along. Now, that's only half of this question. And they don't ask the intermediate question that's necessary to solve it. This question isn't actually asked in the write-up. In the write-up, they simply ask about the energy. But you would need to do this part first. That's what's hard. And that's what I'm trying to emphasize, is that in this problem, the momentum is conserved, but the energy won't be. The bug does work on the disk when he walks on the disk, and the disk does work on the bug, and it's not equal amounts. So the change in energy of this system is going to increase or decrease because work is done. Now, to figure out what happens, you will need to compare the kinetic energy before with the kinetic energy after. You need to compare them. It's hard to know what's going to happen to the energy. In this case, we know that the moment of inertia is going to get bigger and the speed's going to get smaller. However, with energy, speed is more important than inertia because the speed is squared. So usually, energy follows speed, not inertia. So if the speed gets smaller, the energy probably gets smaller too. Meaning the momentum won't increase enough to compensate for how much the speed changes when you square it. So generally, the energy follows the speed. You should figure out how much the energy changes, though, by looking at the difference in the speeds, which would mean in the energies, 1/2 I omega squared, and compare that with 1/2 I omega squared. Compare these two, both before and after. You might be asked to figure out how much the energy changed. That's their difference. You might be asked how much work was done. That's still this. It should be known to you that if delta K is positive, then you did work on the system. You gave it energy. If delta K is negative, you took energy out of the system. I'm telling you all the things you'll need to be able to do on your test tomorrow, or test on Wednesday. Now, I can put the numbers in there, but you guys tend to get blinded by that instead of focusing on the bigger picture here. This problem has, I'd argue, 4 things you need to be able to do. First, you'll need to be able to know how the inertia of the object changes. Second, you'll have to determine if momentum is conserved. No external torque means momentum is conserved. You'll likely have to use conservation of momentum to calculate a velocity. And you'll likely have to compare energies. Now, the reason this problem isn't a good example for your test is because it's largely very algebra focused. And so our answer isn't pretty. It's going to have lots of letters in it. And although I think it's a valuable experience for most of you, I think some of you will be blinded by how many letters there are. And it will simply start to look like it's blurring together. Now, I'm not saying it's not appropriate for us to look at it. I'm saying don't get too thrown off by what you're going to see. So let's take a look at the answer. I before is 1/2 md rd squared plus md squared. This is the I before. They give us frequency, and it's important that you hear this. Frequency is revolutions per second. We want radians per second. So to make frequency omega, you have to multiply by 2 pi. Because that's how you would change something from revolutions to radians. That doesn't make much of a difference in this problem, but I'm just being very clear. Afterwards, the moment of inertia changes because the bug walked to the edge of the disk. The disk doesn't change, but where the bug is, does. This is I after. Omega after is going to be 2 pi times the frequency final, which is what they ask for, the final frequency. So we've written the 2 rotational inertias of the disk, and we've created an expression to figure out the final frequency of the spinning disk. We could solve for it. You guys see how you would solve for it? It's not pretty. And there's no way to pretty it up. So I don't want you to think that you have to. It's going to be 1/2 m disk r disk squared plus m times d squared over 1/2 mass of the disk r for the disk squared plus m r for the disk squared times the initial frequency equals the final frequency. There's nothing pretty about that at all. Then, if we go on, it says, determine the change of kinetic energy in going from the initial to the final situation. Okay. Change. K final minus K initial. 1/2 I final omega final squared minus 1/2 I initial omega initial squared. Now this is going to look messy, Are you sure you're ready for this? All right. Here we go. I'm going to need some space. So here's the space. 1/2 I final and that's the moment of inertia of the disk and the bug at the edge of the disk. Omega final, you'll love this. I have to come back and get this and put it here. All right, look. So I had to plug all because I need to put in omega final. And omega final is based on this frequency times 2 pi. So I got to put all that in there. It's really messy. That's why I told you this is probably not ideal. It's okay for homework, but it's not great otherwise. There's all that times Fi times 2 pi squared. Minus 1/2 times 1/2 mass of the disk, R for the disk squared, plus mass of the bug, distance squared, times 2 pi times F initial squared. It's just icky, isn't it? Now you can combine like terms. Good luck. There are some terms to combine. I would probably just give you the numbers on a test, and that would make this look much easier.